Slow decay or oscillating coherence, non-Markovian. 1. Concept in plain words. In non-Markovian dynamics, the environment doesn't forget quickly. When the system interacts with it, information and phase correlations don't just leak out permanently. Some of them can come back later. So instead of a smooth exponential decay of coherence, we get revivals or oscillations. Physically, it's as if the system sends out a quantum ripple into the environment, and that ripple reflects back, partially restoring coherence. Mathematically, this happens when the memory kernel K evaluated at the difference between T and T prime oscillates or decays slowly, so the integral term in the evolution equation can add coherence back instead of always removing it. 2. Graphical behavior, described. If we plot the magnitude of the off-diagonal element rho 01 of t versus time, in the Markovian case, it's a smooth exponential decay, a falling curve that never rises again. In the non-Markovian case, the curve shows wiggles or bumps, places where the coherence revives after partially decaying. It might dip down, rise back up a little, a partial recovery, then decay again. Each revival corresponds to the environment briefly returning some information to the system. 3. The intuitive picture. Think of it like throwing a pebble into a pond. In a Markovian world, the ripples spread out and never come back. Information is lost forever. In a non-Markovian world, the pond has edges or reflections. Ripples bounce back and interact again with the pebble, temporarily reviving motion. That's what happens to the system's coherence. It returns partially as the environment feeds back. Intuitive summary. The Markovian line is a quiet fade-out. The non-Markovian line is a fading echo, showing that the system and its environment are still talking to each other as time passes. Why this matters? Quantum biology. Processes in light harvesting complexes in plants might use non-Markovian environments, where K evaluated at the difference between T and T prime oscillates, to preserve and even enhance quantum coherence for efficient energy transfer. Quantum computing. Engineers fight decoherence by creating environments where K of T minus T prime is as close to a delta function as possible, no memory. But understanding non-Markovian dynamics is key to building better error correction and even using the environment to our advantage.